Hello everyone. Today we will be looking at limits at infinity. We have done a lot of things in applications of differentiation so far. So let me just go over some of the topics first with you. We have covered and what we are going to be covering in this session. So in the last lecture, we learned how to find open intervals for increase or decrease of the function where the function was concave up or concave down. In this lecture, we're going to be looking at finding the limits at infinity. Now, also we will be looking at horizontal asymptotes, if they are present for the graph of the function, and then finding infinite limits at infinity. The first one was finite limits at infinity, and the other one is going to be infinite limits at infinity. So let's look at first, what do you mean? What are we looking at in terms of finite limits at infinity with the help of a graph of a function? So here we are studying the end behavior of a function on an infinite interval. So let's look at the graph of the function 3x squared over x squared plus 1. So clearly on this left-hand side of the slide, we can see that as x is increasing or x is decreasing, the function value is kind of approaching the 3. You go, as x keeps on increasing, it's going to approach 3 but never touch it. Similarly, as x is decreasing, it is approaching 3, remember, but it's never going to touch it, or neither it's going to be crossing it. So this is like a horizontal barrier for it. You know, like the orange cones we see on the highways, that means you cannot cross them. That's exactly like this little barriers we have. Okay, this was graphically. Let's look in terms of numerics. It's the same function I'm picking up. Now, once again, we will study the behavior of the function at the end on an infinite interval using tables. Now, the table clearly suggests it's the same function, guys, what we just looked at. So x, as you increase the values, say -1, -10, -100, and so forth, notice how the values are approaching very close to 3 if x is decreasing. Or if my x is increasing, you say take 1, 10, 100, once again the values are approaching 3. So what we see is this limit of this function as x approaches infinity or negative infinity is 3. Okay, so we had it graphically here, the 3x squared over x squared plus 1. We also have it here. So here, notice what is the function is 3x squared over x squared plus 1 as x tends to positive infinity or negative infinity. Let me just write it more clearer for you guys. Okay, so the limit as x tends to plus minus infinity, the function 3x squared over x squared plus 1, we notice, is approaching the number 3. Okay, so just look at the pedantic definition of the limits at infinity. What we notice is, suppose as my x values increase, the function it's wiggling a little bit, but after certain times it settles down towards L. Okay, so that's the finite limits at infinity. So what does it says is, if L is a real number, the statement, the limit as x approaches infinity for any function is equal to L, simply means if I take a very, very small epsilon, which is positive, I will be able to find an m, which is again a positive number, such that the difference between fx and L, this is my function, remember the black curve here is the function, and it says as my x is going bigger and bigger, the function, the distance between the function and the L here. So you see this function in L, so it started from here. So this is I'm looking at. It is coming closer and closer over here, it's becoming smaller and smaller. That's less than epsilon. Similarly, if my x is approaching negative infinity, that means for epsilon greater than 0, there exists an n such that the distance between fx and L is still less than epsilon whenever x is still less than n. Okay, so what we really need to know is the next theorem, which is very important for us. This theorem says that if r is a positive real number and c is any real number, then the limit as x approaches infinity of c over xr is 0. Think of the simple example. 1 over x as x approaches infinity. This is the classical reciprocal function. We know that as x approaches infinity, the limit is 0. Notice the graph. What happens over here? As we are coming closer, when the x is increasing, this function is coming closer and closer to 0, but it's never going to, touch 0, but very, very close to 0. That means this number becomes huge. 1 over a huge number becomes very, very small. That's the same as x decreases. That's the classic graph of this function. And that's what it says. Now, if you increase x to, say, x squared, square rooters, anything, this number will still approach 0. Okay? Now, another one, x approaches negative infinity when x is negative. So it's the same example I'm using over here. Okay? It's important that this r should be positive, because if this r is negative and in the denominator, it's going to go over in the numerator and become positive. Then we're not going to get 0. Rather, we're going to get an infinite value. We'll talk about that too. Now, time for examples. Okay, so let's look at this first. This is the scenario. It says, find the limit as x approaches infinity of this expression 7 plus 5x over 4 minus 2 cube root of x. Now remember, this is, we are going to apply what we have learned in very early in the limits chapter, that the limit of a sum of our functions inside an expression is the individual limits of that. So that's what it's doing. So limit of 7 plus the limit of 5 over x4 minus the limit of 2 over cube root of x. Now this one, 4, x approaches infinity, anything which is in the denominator becomes large, then 5 over that number will also become very, very small. So this is approaching 0. Now minus here, but what happens? Cube root of x. This one again is a positive. It's x to the power 1/3. So this one, remember, is 2 over x to the power 1/3. So it will take a little bit more time than to approach 0, because x4 is going to be at a higher values as x increases, but this also is going to approach 0. So the final answer is this number is a constant. So the limit of anything is just going to remain the same. It's never going to change. So you're going to have 7 plus 0 minus 0. So this is where we just applied the formula we have learned, that limit of c over x to the power r as x tends to infinity is 0. This r should be a positive real number. Very, very important. Okay? Plus minus infinity, it's always going to be the same. Okay, so the answer for this example is a 7. Now let's look at another example, some trick here. Okay, we like to find the limit as x approaches infinity of sine x over x. Now to do this problem, remember the first thing, your sine function is a bounded function. The sine values are between minus 1 and 1. So let's look at the graph of our sine function. Things we have learned long time ago, guys, okay? This is how the graph goes, if you remember. Okay? The sine function, if you remember, lies between 1 and minus 1. That's where the sine function is. It never goes beyond that. Okay? So this is 1 and minus 1. So your sine function is always bounded between minus 1 to 1. Now, if you divide this value by x, okay, what happens? So minus 1 over x less than equal to sine x over x less than equal to 1 over x. Now x keeps on x keeps on increasing. So the limit of x approaches infinity of minus 1 over x, we know, is going to approach 0. Similarly, this limit as x approaches infinity of 1 over x is also going to approach 0. So what happens? By the squeezy principle, remember the chapter on limits, that's where we did something like a squeezy principle. If the function sin x over x, which is bounded by minus 1 over x and 1 over x, if the outside bounds are approaching 0, so the function which is in between will also approach 0. Okay, so very important. This is an important kind of a theorem you can assume. So if x approaches infinity, sin x over x is always 0. Similarly, if you take limit as x tends to infinity, cosine x over x is also 0. The reason is because cosine function, guys, remember, is also bounded. And then the same theory, which we have just used here, can be applied to. So sin x over x is 0, cosine x over x as x tends to infinity. So that's why we're saying limits at infinity. Okay, so this is what the theory here is. Now let's look at some horizontal asymptotes. Okay, what's a horizontal asymptote? Asymptote, as it means, is your function cannot cross that line and it is going to be horizontal. Okay, so what's in calculus, it means if I have a function, when I take the limit of that function going either plus or minus, it approaches a real number where L is a real number, remember. Then y equals L is a horizontal asymptote of f. Now, do you remember the example which I just started with the session on was the graphical interpretation of the limits at infinity. So that was again, that had y equals 3. I'll just talk about it. Let me finish this one and I'll go over there. So what happens? When I take the limit of this function, which is 5 minus 2 over x squared, notice this expression is going to go to 0. So the limit of 5x, which is plus minus infinity, is 5. This 5 is like a horizontal barrier. So y equal to 5 is the horizontal asymptote for the function 5 minus 2 over x squared. Very similar to what we just started the graphical interpretation, where I just used the word horizontal barrier. So in this one, notice y equals 3. Remember the limit, graphically we see that y equal to 3 is the horizontal asymptote. Okay? Now, let's look at some rational functions now. Now, to do the rational functions, there's a little theory we talk about, and we're going to do a trick here. Okay? Now, I want to evaluate the rational functions at infinity. What's a rational function? It is a polynomial over a polynomial. Okay? Now, we're going to take the limit of this function x approaches plus minus infinity of a polynomial over a polynomial. Now, to do these problems and see what they look like, what we do is we divide the numerator and the denominator by x to the power k. Where is this k? K is the degree of qx. Okay? Now let's go ahead and do an example now on rational function. So the function is 2x minus 1 over x plus 1. Now clearly this is a rational function because it's a polynomial. It's a linear function on the top and a linear function in the denominator. It's a polynomial over a polynomial of degree 1. When I apply the limit individually, what do you see? When you put it over this is infinity over infinity. Now, not getting us results, okay? So we're going to learn certain other things. Now, if you remember, this is what? So if it is infinity over infinity, this is an indeterminate form. And if you also recall from chapter on limits, we had an indeterminate form of the kind 0 by 0, and we were looking at the limits which were x approaching a finite number. So this is the second indeterminate form we are encountering. So let's look at these rational functions. Let's go back to this problem. First, let's look at it from a graphical point. Notice what is happening. As the moment you see x plus 1, you already know there's a vertical asymptote when x is minus 1. So there it is. That's a vertical asymptote we have. But not only that, the graph shows that there is a horizontal barrier, and that barrier is given by y equals 2. Okay, so graphically we can see it, but analytically we're going to learn how to prove it. And what was this theorem saying? The theorem was saying that if you have a polynomial over polynomial, we will divide the numerator and denominator by x to the power k, k the degree of the denominator polynomial. Okay, so keep this perspective. What is the degree of the polynomial? 1. So what you're going to do, according to that theorem, so we're going to divide the numerator, this, divide by 1 over x, or sorry, multiply or divide by this whole expression by x, multiply by 1 over x, or also divide x plus 1 by x. Okay. Now, let's do the math on the next slide. So, remember, according to this, the degree of the denominator is 1. So what we do is we divide the numerator by x to the power 1 as well as the denominator by x to the power 1. And then we do simple calculations. So this means you're having 2x over x minus 1 over x. What do you get? 2 minus 1 over x. In the denominator, you get x over x plus 1 over x. You get 1 plus 1 over x. Now you can take the limits inside. So the limit of 2 as x tends to infinity minus the limit of x tends to infinity of 1 over x. And then the denominator limit of 1 x tends to infinity plus the limit of x of 1 over x. Now these two limits are going to 0. The limit of 2 is a 2, limit of 1 is 1. So your final answer is 2. So this limit of a rational function is equal to 2. That means y equal to 2 is a horizontal asymptote. Not only we have found the limit of a rational function at infinity, but also in the process we figured out a horizontal asymptote. Now let's look at another function. Now here our function is 1 over x squared plus 1. Now this is again a polynomial. It's a constant polynomial, and the denominator is a quadratic. So what we notice is, now we're going to do is, okay, again it's a 1 over infinity form, by the way. But remember, if you have a polynomial over a polynomial, that means you have a rational function. You look at the denominator of the the degree of the denominator polynomial. That's a 2. So you're going to divide 1 by x over 2. Similarly, you will divide x squared plus 1 over x squared. That's the theory we do. And so what we get is 1 over x squared. This will be 1 plus 1 over x squared denominator. Then you take the limits inside. So when you take the limits inside, the limit of the numerator is 0. And the limit in the denominator is 1 plus 0. So 0 over 1. So the limit is a 0. So what we see of this, even from the graph, you can say the function has a horizontal asymptote at y equals 0. So y equals 0, the x-axis is a barrier. Okay, let's look at another function. Here is a function where the limit, we have a rational function again, 8x cubed minus 5 over 4 minus 9x. Now, when I look at from the graph, clearly as x tends to infinity, the function also keeps on increasing. It's not reaching an infinite number. So, according to the picture, it is approaching infinity. Okay, and it's approaching negative infinity because it's going down, down, down. Now, let's do the math. You have a cubic in the numerator and a linear function in the denominator. So according to the theory, we will divide the numerator and the denominator by the x, because the degree over here of this function, the denominator is 1. So we will divide this by x, that is, we will have 8x cubed minus 5 over x. Similarly, the denominator will be divided by x, which is in the next step. Now, what we're going to do is, we're going to simply do our calculations. You will have 8x squared minus 5 over x, 4 over x minus 9. So clearly, when you take the limits inside, this goes to 0, 4 over x goes to 0. What are we left with? 8x squared. So as x increases, 8x squared also increases. So you have an infinity on the top, but a negative 9 in the denominator. So infinity over negative 9, no matter how big the number is, even if you divide, it's still going to be a very big number. So the final answer is negative infinity. Okay, so we have three scenarios we're looking at. The first scenario, you're getting the value to be 2. The second scenario, notice you're getting to be 0. And the third, you're getting to be an infinity. Okay, because that means the limit is not existing. Please remember, this means limit does not exist. That there is, we cannot define it, okay? So that's the scenario. We cannot define it. So once it's, if you remember, this one means decreasing without bounds. Again, in chapter on limits, I'm saying here. So that means limit does not exist. So we just write negative infinity. Okay. Now, the things to also keep in mind is that in this scenario, the numerator degree was greater than the denominator degree. Okay. And we got the limit is not existing. The degree of the numerator here is less than the degree of the denominator. You get a 0 as the limit. And this is a very powerful observation, guys, what I'm talking about. And if the degree in the numerator and the denominator is the same, the answer actually is the coefficients of the numerator divided by the coefficient of the denominator. It's 2 over 1. Do you see this one? So these three are really, really important for us in limits at infinity. Okay, let's take another example. We have some trick here too. The limit as x approaches infinity of 6x squared minus 2x sine x, 6x minus x squared in the denominator. You have the graph here. Notice what happens. As x is increasing, the function is approaching a certain limit. So that value is, this is where the function is going. It's just approaching, it's never going to cross. You will notice when we do the analytical approach here, you'll get negative 6. So let's do the math here. First of all, you look at this function. You notice the denominator has a degree 2. So what you're going to do, you're going to divide the numerator by x squared. So you're going to divide this by x squared and also divide the denominator by x squared. You get this next expression. 6x squared minus 2x sine x over x squared, 6x minus x squared over x squared. Now, basically, pull apart all the expressions in the numerator over here. Similarly, you do it in the denominator. What do you get? 6 minus 2 sine x over x, this is 6x over x squared, which is 6 over x. So this is basically 6 over x minus 1. Notice, then you take the limits inside. And when you take the limits inside, remember this limit, this we just said, as x tends to infinity of a sine function over x is 0. So that means this is going to 0. This will go to 0. What are we left with? 6 and minus 1. So we get left with 6 over minus 1. Final answer, y minus 1. So y equals minus 1 is the horizontal asymptote for this function. Okay. This is the most important observation for us, guys, which I just talked about also a few minutes earlier, that if the degree of the numerator is less than the degree of the denominator, the limit of the rational function is 0. On the other hand, if the degree of the numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficients. And third, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. Remember, we get plus minus infinity as the answer. We did that earlier too. So now, my recommendation to you guys is practice these problems. Very important. You need to practice these problems. Thank you.